So, in this lecture we shall study linear transformations, isomorphisms and matrix representation of linear transformations. Actually, when we compare mathematical structures of same type, that time we study some order preserving mappings, and such order preserving mapping in case of a linear algebra are called linear transformations. So, let us define this linear transformation. So, let V and W be vector spaces over same field F. A mapping T from V to W is called a linear transformation if the following hold. That first condition is that T of u plus b is equal to T u plus T b for any vectors u and v in the vector space V. Here of course, this plus operation in the left hand side represents plus operation in the vector space V, and this plus operation in the right hand side represents plus operation in the vector space W, or in other words this first condition means that this mapping T preserves addition operation of the vector space. Here T of alpha u is equal to alpha times T u for u belongs to the vector space V and alpha comes from this field F. This second condition is also means that this mapping T preserves scalar multiplication. Combiningly, this first and second can also be written like this. So, combiningly first and second can be written as for u v belongs to vector space V and alpha beta belongs to F T of alpha u plus beta v is equal to alpha times T u plus beta times T v. One can check this condition also for checking whether a mapping T is a linear transformation or not. So, let us see one example that let us check. So, let T1 and T2 be mappings from R3 to R2 defined as T1 of x1, x2, x3 is equal to x1 plus x2 and x3, T2 of x1, x2, x3 is equal to x1, x2, here x3. We shall check whether T1 and T2 are linear transformations or not. So, this T1 is a linear transformation because T1 is a linear transformation because it preserves addition and scalar multiplication like T1 x1 x2 x3 plus y1 y2 y3 is equal to T of x1 plus y1 x2 plus y2 x3 plus y3, and according to this is T1. So, according to definition of T1, it is like this: x1 plus y1 plus x2 plus y2 x3 plus y3, and this can be written as x1 plus x2 x3 plus y1 plus y2 y3, and that is equal to T1 of x1 x2 x3 plus T1 of y1 y2 y3. So, T1 preserves addition operation, and similarly T1 also preserves scalar multiplication because T1 of alpha times x1 x2 x3 that is equal to T1 of alpha x1 alpha x2 alpha x3, and according to definition of T1, this is equal to alpha x1 plus alpha x2 alpha x3, and this can be written as alpha times x1 plus x2 x3, and that is equal to alpha times T of x1 x2 x3. So, therefore, T1 is a linear transformation, but one can check that T2 is not a linear transformation, that T2 is not a linear transformation, because it does not preserve addition. Of course, it does not preserve scalar multiplication also. So, because T2 of x1 x2 x3 plus y1 y2 y3, this is equal to T2 of x1 plus y1 x2 plus y2 x3 plus y3, and according to the definition this is equal to x1 plus y1 into x2 plus y2 x3 plus y3, and of course, this is not equal to x1 x2 x3 plus y1 y2 y3. So, therefore, this T2 is not a linear transformation. So, linear transformations are very useful, and here we have one specific type of linear transformation, that is called isomorphism. So, that here we consider again vector spaces V and W be vector spaces over the same field F. A linear transformation T from V to W is called an isomorphism. If T is 1 to 1 and on 2. If there is an isomorphism from V to W, if there is an isomorphism from V to W, then V and W are called isomorphic. So, isomorphic means that V and W have same structure, algebraically they have the same structure. So, for every algebraic structures we consider this concept of isomorphism. This verifies whether given vector spaces have the same structure or not. So, we can have some example of isomorphisms. So, this first is condition is that V is isomorphic to itself because the identity map is an isomorphism from V onto itself. So, another example is that every finite dimensional n dimensional, we can say every n dimensional vector space is vector space over R is isomorphic to R n. Of course, we will see some more example of isomorphisms later on. So, here we will see some properties of an isomorphism, that properties of an isomorphism. So, if first properties are like this, if T from V to W is an isomorphism, then T inverse from W to V is also an isomorphism. So, for any linear transformation, we have for any linear transformation T from V to W, image of the 0 vector, that is T 0 is the 0 vector again, and further if T is an isomorphism, then further if T is an isomorphism, then T of V equal to 0 implies that V is the 0 vector. And third property is like this, that an isomorphism, third property says that an isomorphism maps a linearly independent set to a linearly independent set. That is, if T from V to W is an isomorphism and S is consist of a set of linearly independent vectors. S is consist of vectors v1, v2 to vk is a linearly independent set, then this image of S, T S, that is T of V1, T of V2, T of Vk is a linearly independent set, linearly independent set. So, of course, this property we have already given in the example. Here this theorem gives a result which checks whether when two finite dimensional vector spaces are isomorphic. So, the result is like this: two finite dimensional vector spaces over the same field, F are isomorphic if and only if and only if they have the same dimension. So, this gives a criteria for checking whether finite dimensional vector spaces over the same field are isomorphic or not. So, next we shall see another important point, that we defined some spaces associated with a linear transformation. They are called range spaces and null spaces. So, they play an important role. So, let us have this definition, that let T from V to W be a linear transformation then the kernel, we define the kernel of T denoted by ker T is the set kernel of T is consist of all vectors in the vector space V such that T of V is equal to 0, and this set, that is T of V that is consist of T of V such that V belongs to V is called the range of T, and if this T is So, if for any linear transformation T, we have this result, one can check easily that for any linear transformation T from V to W, kernel of T is a subspace of V, and second result is that range of T is also a subspace of W, that one can check easily by using the definition of a linear transformation, and it is not hard to check. In fact, we can also give briefly proof of this. The first one is, say we have to consider that vectors u and v in kernel of, so let u and v belongs to kernel of T, and alpha beta they comes from the field F. So, this T of alpha u plus beta v, that is equal to alpha times T u plus beta times T v, this is equal to 0. So, this implies that alpha u plus beta v belongs to this kernel of T, and hence kernel of T is a subspace. Hence, kernel of T is a subspace of V. Similarly, one can also prove this range of T is a subspace of V. So, let W1, W2 belongs to this range of T, then there exist vectors V1, V2 in the vector space B such that T of V1 is equal to W1 and T of this V2, T of V2 is equal to W2. So, we shall show that this for any scalars alpha beta in F, we show that alpha W1 plus beta W2 belongs to range of T. So, now the image of that alpha V1 plus beta V2 is equal to alpha W1 plus beta W2. So, since this alpha V1 plus beta V2 is an element of V, we get that alpha W1 plus beta W2 that belongs to this range of T. Hence, this range T is a subspace of W. So, here we give this another definition that the dimension of kernel of T is called nullity of T, and dimension of range of T is called the rank of T. So, here we are having an important result that relates this nullity and rank and dimension of the vector space. Of course, the dimension of the vector space has to be finite. So, that result is known as this rank nullity theorem. So, this is a very famous theorem called rank nullity theorem. So, let V be a finite dimensional vector space, V be a finite dimensional vector space with dimension of V be equal to n, then for any linear transformation, T from V to W, we have the following relation. We have this following relation, that nullity of T plus rank of T is equal to dimension of V. So, of course, one can prove this theorem easily. It is not difficult. We will give here outline of proof of this theorem, outline of proof of the theorem. So, here one considers that since dimension of B is finite, that dimension of kernel of T also finite. Let dimension of kernel of T, that is also nullity of T, be equal to k. Okay. This is, that is, k is the nullity of T, and V1, V2 to Vk be a basis for kernel of T. Of course, this k is less than or equal to n. So, now this basis of kernel of T can be extended to a basis of V. This basis can be extended to a basis for V, say V1, V2, Vk, Vk plus 1 up to Vn. Then one checks that this T of Vk plus 1, images of these vectors Vk plus 1, Vk plus 2 up to T of Vn is a basis for range of T. Hence, the rank of T is equal to n minus k, and we get the result. So, this Rank-nullity theorem is also very useful. So, next we shall see matrix representation of a linear transformation, that is matrix representation of a linear transformation. So, here we see that every linear transformation can be expressed as a matrix, and every matrix gives a linear transformation, or there is some sort of correspondence among matrices and linear transformation. So, sometimes people refer matrices as linear transformations also. So, first here we shall see from matrix to linear transformation. So, this matrix to linear transformation. So, here we are having a matrix m by n matrix. So, say A with entries A I j be an m by n matrix over, let A be a matrix over a field F. Then we will find a linear transformation associated with this matrix. So, here recall that an n dimensional vector space over F. So, we consider that, so let V be n dimensional vector space, n dimensional vector space over F. Then elements in V can be written as n tuples of elements in B, or that is n minus 1 matrices over F, that is x 1 x 2 up to x n. Here x i's they come from F, and similarly let W be an m dimensional vector space over F consisting of elements of the form x 1 up to x n x m with x I comes from F. Then we define a mapping, say T, from V to W as T of any element x 1 x 2 to x n as this matrix A, which is m of size m by n, and that is multiplied by this matrix x 1 x 2 to x n. So, this is a matrix multiplication and its resultant will be an m by 1 matrix, or that is an element of W. Then easily one can verify that T is a linear transformation. Then T is a linear transformation. This can be checked by applying properties of this matrix A also, and this is how we get a linear transformation T from given any matrix M. Notice that if A is a matrix of size m by n, then we get a linear transformation from an n dimensional vector space V to an m dimensional vector space W. So, next we shall consider the converse of this, that is from linear transformation to a matrix, that converse of this from linear transformation to matrix, or in other words we see matrix representation of a linear transformation. So, here we consider this a linear transformation. Let T from V to W be a linear transformation where dimension of V is equal to n and dimension of W is equal to m, and we consider bases in the vector space V and W. So, let this V 1, V 2, V n and W 1, W 2, W m be bases for V and W respectively. Actually, we find matrix representation of linear transformation T with respect to these bases. That means, we fix a basis in the vector space V and a basis in the vector space W, and with respect to these two bases we find matrix representation of this linear transformation. So, here we find the matrix corresponding to this linear transformation like this. So, T of V 1, we shall see images of the vectors V 1, V 2 to V n with respect to this linear transformation. So, T of V 1 is an element in the vector space W. So, therefore, T of V 1 can be written as a linear combination of the basis vectors W 1, W 2 to W n, W m. So, let us consider that linear combination be like this. T of V 1 is equal to A 1 1 W 1 plus A 1 2 W 2 plus A 1 m W m, and T of V 2 is A 2 1 W 1 A 2 2 W 2 plus A 2 m W m. Like this, T of V n, image of V n is equal to A n 1 W 1 plus A n 2 W 2 plus A n m W m, sorry, this is W m. So, here all these Aij, where all these Aij, they are in the field F I from 1 to 2 n and j from 1 2 to m. they all belongs to this field F. So, now from this expression, this we find the matrix corresponding to the linear transformation T, and it is like this, that now the matrix corresponding to the linear transformation, the linear transformation is actually this matrix, that here we consider the coefficients of first linear combination as first column, that A11, A12 and this A1n, A21, A22, A2n and like this AN1, AN2, ANM. So, this is this matrix. Here we are having this basically in one, okay, this is one A1m, okay, sorry. So, this 1m, 2m, ANM. So, this is basically an m by n matrix. So, size of this matrix is m by n. So, here we will consider an example how to find this matrix representation of a linear transformation. You notice that if we consider different bases for the vector spaces B and W, then we may get different matrix corresponding to this linear transformation. Of course, those matrices are not totally different, they are also related, and they are in fact similar, and that we are not going to prove. So, let us see one example here. So, consider this example. First example is that we shall consider a matrix and from there we get a linear transformation. So, that is find the linear transformation, find the linear transformation associated with or corresponding to this, corresponding to the matrix, say that is 1 3 minus 2 0 4 1. So, here this matrix is of size 2 by 3. So, we get a linear transformation from R 3 to R square. So, the corresponding linear transformation. So, let T be the corresponding linear transformation which is given by, so T is basically a linear transformation from R 3 to R square, and T of any x 1, x 2, x 3, that is given by 1 3 minus 2 0 4 1, that we multiply with this x 1, x 2, x 3, and we get this as x 1 plus 3 x 2 minus 2 x 3, and here we get this 4 x 2 plus x 3. So, this is the linear transformation associated with the given matrix. Then example 2 is like this. Here we consider a linear transformation. Consider the linear transformation T from r cube to r square defined by T of x1, x2, x3 is x1 plus x2 twice x3. We shall find matrix representation of this linear transformation. Matrix representation of this linear transformation. So, here we this linear transformation with respect to the basis, say that is B consisting of 1 1 0 0 1 4 1 2 3 and B prime is consist of 1 0 0 2 of R3 and R square respectively. So, now we shall find image of this basis vectors, that T of 1 1 0, that is according to definition of this linear transformation, this value is 2 0, and that can be written as linear combination of basis vectors in the range space is like this: 2 into 1 0 plus 0 times this 0 2. Image of the next basis vector, that 0 1 4 is 1 8, and this can be written as linear combination of basis vectors in R2 or in the range of T s 1 times 1 0 plus 4 times 0 2. Then image of 1 2 3 is 3 6 from the definition of this T, and this can be written as 3 times 1 0 plus 3 times 0 2. So, now these coefficients, from these coefficients we get the matrix of T. Now, the matrix corresponding to T is given by that 2 0 1 4 3 3, or in other words that also we can think as transpose of this coefficient matrix. So, this is how we find matrix representation of a linear transformation. So, of course, here we are getting this matrix representation of a linear transformation with respect to some bases. If we change these bases in the domain and range space of this T, then we get different matrix. Okay, that's all for this lecture. Here we stop. Thank you.